Okay, before we get started on this video, I realized on the last two videos that I made, they're a little echoey, and they actually have some issues where you can hear my pen on the tablet. That's because I was mistakenly using the webcam. Well, it wasn't the camera, obviously, it was the speaker, but I was using that as a method for recording my voice, and so it's a little echoey and everything. But I looked at the videos, and I feel they're still good enough that you can still understand everything that's going on. But now I'm actually using my gaming headset for recording the audio, which does a much better job than the microphone for the webcam. Alright, so now what we're going to look at here is we're going to look at active loads with MOSFETs. And so we're going to start off the same way we did with bipolars, is we're going to look for the small signal, not small signal, this is the open circuit voltage gain. Now, first thing we should point out here is that, to set up IREF, we had another transistor that acted like a resistor. And also the other thing we should recall is that here, let's draw these here. I'll call this I2 since I'm by the 2. So this again would be M1, M2, M out. That I2 and IREF's relationship depends on the aspect ratios. If the aspect ratios are the same, we got that I2 was equal to IREF. But if they're not the same, we got something a little bit different. Okay, so let's go ahead and do some analysis here with this. So first off, let's label some things here. So we have plus, let me use a different color to label. Plus minus VSD1. And then we have plus minus VSD2. And then we have plus minus VDS out. And of course we have I out as well. And then we have this VSG. Because remember, because of this being tied here, VD, and then we also have that these two voltages are the same. VGS is the same for these two MOSFETs, so we get our nice biasing here. So we're going to assume that M1 and M2 are identical. So if we have that they're identical, we have that lambda 1 equals lambda 2, and that's going to be lambda p, that's what we'll call it. The turn-on voltage is equal to the turn-on voltage, which is equal to VTP, and then of course KP1 equal to KP2, which is equal to KP. So that means the aspect ratios are the same because the aspect ratios are, quote, hidden in these K constants. Remember that K itself is mu n Cox over 2 times my aspect ratio. So if we're saying those are the same, those are matched. So we have that here, that IREF equals I2, which equals I out. And then we're going to do the same kind of analysis we did with the bipolars. I'm not going to show all the details on it, but I will write some of the equations down for us here. So we have then that, for instance, I1, which is equal to Iref, would be equal to Kp times VSG plus VTP squared times 1 plus lambda p VSD1. And if we go back here on the circuit, we have that VSD1 is equal to VSG. So I could erase this and say that this is VSG instead. And then we'd have I2 is equal to Kp VSG plus VTP squared times 1 plus lambda p VSD2. Now I don't know what VSD2 is. And then finally we have then that I out would be Kn VGS minus VTN squared times 1 plus lambda n VDS 0. So we have all those three equations. They're all equal to each other. And then basically going through a bunch of algebra, which I am going to skip at this point. I'm not going to go through all the algebra, but you could go through the algebra and you would end up solving, because what we should point out here is this VDS 0, this is V out, is that we would wind up with V out is equal to 1 plus lambda p times V plus minus VSG divided by lambda n plus lambda p minus Kn times Vi minus Vtn squared over Iref lambda n plus lambda p. And basically there's just a ton of work that we have to do to get all of that in there. But then just remember here, again, when we wanted to figure out what our voltage gain was for the bipolar, what did we do? Well, to get the voltage gain, we did derivative of the output voltage with respect to the input voltage. And if we do that, again, notice here, this term is just going to go away completely because there's no VI here. So that's just going to be gone completely. And then what we wind up with here is that this would be equal to, well, taking a derivative of this, I'd have a 2 coming down in front, so I'd have negative 2 Kn Vi minus Vtn, and then this is all over Iref lambda n plus lambda p, because the 2 comes down in front. Then you'd have to take a derivative of what's inside, so we'd have to take a derivative of what's inside here. But if we look at that, that's Vi minus Vtn. The derivative of that would just be 1, so I'd multiply by 1. So I'm going to instead just erase that because it's just multiplied by 1. And so there we go, and here is my gain. Now again, we're going to kind of rewrite this a little bit here. We should notice something here. 2 Kn Vi minus Vtn is equal to the transconductance of the M0. And then we can also look at here that, well, we have IREF times lambda n plus IREF times lambda p, and then looking at our equations again here, going back to just our simple ones here, we get that this is 1 over the early voltage resistance for the N channel plus the one for the P channel. So we get my gain equation then, combining this all together, we get that the gain here is negative GM divided by 1 over R on, well, R on, ON plus 1 over RO, that doesn't look like a 1. One over ROP, which we could rewrite as negative JGM times RON in parallel with ROP. And so that is my, again here, this is my open circuit gain. Alright, so let's look at a quick example here with this, because this is going to be, again, pretty easy here. So we're going to look at the same figure, so I'm not going to redraw it, so we're going to use the same figure. And we're going to have these parameters. VTN is equal to 1 volt. VTP is equal to minus 1 volt. KN equals KP, which is 0.2 milliamps per volt squared. Lambda P equals lambda N, which is 0.015 volt to the minus 1. V plus is equal to 10 volts. IREF is equal to 0.25 milliamps. And then we're supposed to find VSG. Part B, we're supposed to find VI. So VDS0 equals VDS2. And then C, open circuit voltage gain. Let's go ahead and tackle part C first here, because again we can do that one already. And just remembering here that RON would be 1 over lambda I out, which would be 1 over 0.015 times 0.25 milliamps. And if I do that computation here, 0.015 times 0.25 milliamps, inverse of that, we get 267 kilo ohms. And so ROP is going to be 1, this should be lambda N, lambda P I2, which is going to just be the same thing because the parameters are all the same. So we get 267K for that. and then GM for the, I'm going to emphasize this is for the output transistor. That's just going to be 0.25 milliamps divided by 0.026. And so if we do that computation, we get 9.62 milliamps per volt. And now we have everything to actually do the computation, because then my gain is going to be 9.62 milliamps, there's a negative here, negative, times 267K, and parallel with 267K. So if we do that computation, I wind up with negative 1284. Okay, so again, this was part C that I did first. Now we need to do parts A and B. I mean, we could have done A and B first. So part A, remember, it's asked me to find VSG, so I'm going to scroll back up here. So we're trying to find VSG here to figure out what this needs to be here. But that's not a very difficult thing to do here, to find VSG. Why is that not difficult to do? Well, what do we know here? We know that, for instance, Iref for part A here has to equal Kp times VSG plus VTP quantity squared. And we know everything in there except for VSG. So my Iref is 0.25 milliamps. I believe that's what we had. Yep. And this is equal to 0.2 milliamps per volt squared times VSG. And then it's going to be plus, and the VTP is -1, so -1 squared. And then just solving this, I'm not even going to show the steps. I mean, this is pretty basic algebra to solve. But if we solve this, let's see, what do we get here? We get 2.12 volts. Okay, so we got 2.12 volts, and then part B is asking, what does VGS 0 need to be so that VDS sorry, I just spaced there for a second. VDS2 is equal to VDS 0. So what that tells us right away is that VDS 0 has to be 5 volts because we have a 10 volt power supply. And so what we have here is we have a slightly, I wouldn't say more complicated, but we need to take into effect the early voltage here. And so what do we get here? Well, we get that ID is equal to Kn VGS minus VTN squared 1 plus lambda n VDS. But again, we have everything in that equation except VGS. What we have here is we got 0.25 milliamps per volt, and then Kn is 0.2 milliamps per volt squared. We have VGS minus 1 squared 1 plus 0.015 times VDS, which is 5 volts. So if we do that and we do all the computations, we get an answer of VGS is equal to, let me do the computation here. I'm not going to show all the work. In fact, I'm going to pause it. You get 2.08 volts. Now, this was doing it precisely, but notice really what did we get here? Part A, we had 2.12 volts. Even taking into account the early voltage effect, we got 2.08 volts. And what do we did when the bipolars? We said, oh, the answer is obvious. So because we want the VDSs to match and everything, and the currents, it is okay to say VGS is going to equal VSG. But I'm going to put a star here. Transistor properties match. If they don't, you have to do a computation. Solve this one. I'm not going to give you the answer. Part B, so we're going to find VGS, but change Kn to 0.5 milliamps per volt squared and VTN to 1.5 volts. You won't get that VGS is the same as VSG because the transistors are no longer matched. So when we say, oh, they're going to be the same voltage, the only reason that we can say they're the same voltage is that the transistor parameters are matched. So I encourage you to do this one. You'll get a different value for VGS. And again, this would be a great problem to put on an exam.